My name is James Bamba, and I'm doing the presentation for phase two of this project. From phase one, I was able to design a route that has a 40-mile design speed from the beginning of the project and then transitions to 25 miles per hour at the end of the project. So this is just a corridor layout of the route that I designed from phase one. The profile for that route consisted of 7% going down to 6.7%, and then it matches road 43 at a very flatter slope of negative 2.83% here. So that's the profile for the route that I'm using for this phase two. This is the plan layout of the route. You can see the route with the tow, and then I also was able to have a clear zone distance of 40 feet. So it's here, and then I was able to meet the minimum horizontal radius and then the minimum step inside distance as here shown in these tables. So the criteria for this curve one is also shown on top here. So this is for 40 miles per hour, and then it's going to transition in the next style, in the next slide, it's going to transition to 25 miles per hour, which is here. So I was able to do that too. I still have my clear zone here, and I was able to make the minimum radius and then the step inside distance from phase one. These are the criteria used for this phase two. We're using the tool. So in designing for phase two, I was able to design for a slope of 4:1, 3:1, and 2:1. As you can see in this diagram here, the 4:1 is steep, is the farthest away, which quite makes sense. And then you have 3:1 and then 2:1. So this is the tool I use, the slope of the tool I use to for my MOE, which I'm going to discuss in the next slides. Again, I have 2:1 tool here. The 2:1 tool runs from the beginning of the project to the end of the project. Likewise, 3:1 and then 4:1. So the 2:1 tool here is steep, and then it will require me to have a barrier because the minimum slope requirement not to have a barrier is 2.5:1. But since I'm having 2:1 here, I need a barrier, and that's going to be shown in my MOE. Like I said in the previous slide, is because my first alternative is 2:1, and because the slope is steep, 2:1, I put the barrier length here, which is the length of the whole project. So that's what I have. 3:1 slope is not that steep, so I do not need a barrier, and I do not include it here. Likewise, 4:1. So I use the cut and fill also using this slope criteria. I use their cut and fill, and these are the numbers I was able to find. I made sure that the cut and fill are quantified together. Like I use 25, sorry, 12.5 for each. 12.5 for cut and 12.5 for fill. So these are the numbers I was able to have. The speed did not change because I still maintained my 40 miles per hour speed at the initial part of the project, and then ended with 25 miles per hour at the end of the project. So nothing changed on that. The area of encouragement, and make sure that I divided into two. One is the area, the reduce real estate impact. I made sure that I divided into two. One is the area of encroachment and the other the land from the real estate. So the area of encroachment, I did not impact the estate at all, even with a 4:1 slope, because that is steeper one. I did not impact the estate at all. So nothing changed in my MOE. So for the land from the toll to the real estate, these are the numbers I was able to have, which quite makes sense here. The 2:1 should be the farthest away from the real estate, followed by 3:1 and then 4:1. So these are the numbers I have. Putting all the last part of the MOE is the angle 90 degrees to the intersection. That did not change as well because from my initial design, the design that I'm using now, I was able to meet the intersection at 90 degrees. So that did not change at all. So from these MOE criteria, I was able to have the least number of MOE, which is 58.5 from alternative two. So alternative two, which is using the side slope of 3:1, is the one I'm gonna use for moving forward in this design. So this is my pavement marking. Since we are starting here from 40 miles per hour, I have the 40 miles per hour. In the long run, during this presentation, you realize that we're gonna have like a matching taper here. So because we're gonna have a matching table here, and make sure that I put this right lane ends, and then this right lane is gonna be shifted to the left. So that's why I also have lane ends match left. It's gonna be match left from a two lane to a single lane here. So these ones are just showing that we have a horizontal curve so that the drivers can reduce their speed in this area. The same, similar to what we from the previous slide. Since we move into 25 miles per hour, I had the 25 miles per hour in both directions for drivers to see, and also the horizontal curve, horizontal curve sign, so that the drivers can know they are going through a bend and they can reduce their speed. I also have the advanced stop sign notice here, so that drivers can be aware that they're coming to a stop. And then this one here, since we are approaching a T intersection, I have this sign here to tell drivers that they can go either north or south. It's not a cross intersection. They cannot go through. That's why I have this sign in here. This is the intersection. This is we are told the truck that's supposed to be using this intersection is an SU40 truck, and these are the criteria given for us. The maximum truck radius of 51.2 and the minimum truck radius of 36.4. So I was able to incorporate all that in this design. So in this intersection here, this truck can safely operate in this intersection. So these arrows here, they are not paving marking though, they are just showing the direction of traffic. This is intersection grading here. The intersection grading also aligns with my profile. My profile did did not impact anything on road 43. My profile ends at this point here and it matches this elevation. So that's why my profile ends. So the intersection grading shows that everything here, the road is grading, is draining down from this point here. Everything is draining towards road 43. So you can see from the contour here, they all have positive impacts. The contour numbers are reducing. So in terms of drainage, I'm having no issue from my road to road 43. Everything is draining from my proposed road to road 43 without having any issue drainage wise. The next slide, like I said, this is the point. This is the point I did my connection to road 43. Again, I did not impact anything on road 43, and my slope is not steep. It's not deep enough. It's flatter here, so I have no issue with my slope. So I was able to connect to the road 43 without impacting the rest of it. So this is the profile just to show my connection point to road 43. Coming back to the side triangle here, the side triangle on the right, since we are transitioning from a single two-lane direction, two lanes, one lane per direction, to a multi-lane, two lanes per direction, from the equation of the side triangle, we needed to add zero point 0.7 to the time gap. So when you add the zero point 0.7 to the time gap and you run the equation, you come out with these numbers here, like the B value of 680 and the A value of 44.5. So that's what I did in this side triangle equation, so that I can have the right offset side triangle as shown in this graph here in this slide. Similar to the left offset side triangle, I was able to do the same thing. We are transitioning from a two lane at the intersection to a multi-lane. So the multi-lane has two lane per direction, and because of that, again, we need to add zero point 0.7 like I did in this table here. So once you do that and you run the equation for a left-sided side triangle, you will able to come out with these numbers as shown here. This is like I talked about earlier. This is the shift, the matching taper. This is road 42, sorry, road 12. Because we are transitioning from a two lane to a single lane, so we are matching to a one lane. So because of that, using this equation, the matching taper and a design speed of 40 miles at this area, we will have like 320 matching taper length. So that's what I have here, has shown at this in this slide. I made sure also that our road 12 is not impacted, and make sure that I have at least 20 feet of buffer before the taper ends. So you can see the 20 foot of buffer here before the taper ends, and the extra 320 matching taper. Final slide is the shifting taper at the beginning of the project. Again, at the end of the project, at the end we are shifting from a single lane to a two lane, and with a design speed of 25 miles per hour, the length for the shifting taper is 125 using this equation here, because the design speed is less than 45 miles per hour. So that's what I was able to use. This concludes my presentation for this phase. Thank you so much. Mm.